In section 2.4, we're going to kind of continue where we left off from 2.3 and cover some more proofs and some more methods of proofing. This first one says, let mn be an element of the natural number set. Prove that if m plus n is greater than or equal to 73, then m is greater than or equal to 37, or n is greater than or equal to 37. So to do this one, I'm going to do the proof by contrapositive. To do proof by contrapositive, I have to write this statement in its contrapositive form. So we did this actually at the end of section 2.2. I let this first part be representing by P, this one by Q, and this part by R. And so the proposition has the form of P implies Q or R, and the contrapositive has the form of not Q or R implies not P. And then I mentioned by De Morgan's law how the not changes it into not Q and not R implies not P. And so the way we write this in words was, if m is less than 37 and n is less than 37, then m plus n is less than 73. But to make this a little bit easier on ourselves, I'm going to go ahead and rather than say less than 37, I'm going to say less than or equal to 36. Would y'all think that would be the same thing as saying less than 37? We can say that the next number down from 37 is 36, since we're not dealing with any in-betweens between the integers and so forth. It also means I can say m plus n is less than or equal to 72. That way it's a little easier to read, because when I say less than 37, it's not exactly clear what number I'm going up to. So here I'm going to be able to say up to and including the number 36 and 72, since we have integers here, so it's all the same. So here's how the proof is going to go. So we can say that we have the property for real numbers that if A is less than C and B is less than, we can say less than or equal to here, D, then A plus B is less than or equal to C plus D. And since this is applies for all real numbers, it's going to apply for the integers we have as well. So we can say thus, if m and n are in the natural number set with m less than or equal to 36 and n less than or equal to 36, then we can see that if we take m plus n, it has to be less than or equal to 36 plus 36, and then that means that's equal to 72. Hence, it's then obvious that m plus n is less than or equal to 72. And so that proves the statement that we were trying to do here. But we use the contrapositive form so that we could start with m and n individually first, add them together, and then show that they have to be less than or equal to 72. And so I guess we could wrap this up, since this was just the contrapositive. We could say by the contrapositive, if m plus n is greater than or equal to 73, then m is greater than or equal to 37, or n is greater than or equal to 37. A logically equivalent statement to what we just proved. Now here's an interesting statement. It says, prove that the square root of 2 is irrational. Okay, this is something that we can't take for granted based on the definition of rational numbers. Basically, the definition of a rational number is a number with p over q such that p and q are an element of the integer set and q is not equal to 0. So if square root of 2 is irrational, it cannot be written as a p over q number with p and q being integers. However, if it is rational, then there should be a way of finding p and q to make it look like it in that form. So what we're going to do is prove that that's impossible to do. It's impossible to write it as the form of a rational number. And the way we're going to do this is proof by contradiction. So what do we mean by proof by contradiction? We're going to start out by assuming the contrary to this proposition above. So we want to assume rather than irrational, we're going to start off with assuming that the square root of 2 is rational. Okay, so that's the very first thing that we say here. Assume that square root of 2 is rational. Okay, so since we say that this thing is a rational number, there should be things we can assume about it now as a result. If the square root of 2 is rational, then we should be able to know that there exists a rational number x such that x squared is equal to 2. Also, we can say now, by definition of rational numbers, x has to be equal to p over q for integers p and q, with q not equal to 0. Also, we can assume that this fraction is in its lowest terms. So we assume that p over q is in its lowest terms. And as a result, if it's in its lowest terms, then p and q must have no common factors except 1. Okay, so now we know some things about it. Let's see if we can continue on from here. So now we can say since 2 is equal to x squared, and x squared is the squaring of the p over q, then x squared must be p squared divided by q squared. And that means we have p squared is equal to 2q squared. So thus, as a result of seeing that p squared is equal to 2 times q squared, we have to know that p is an even number. It's a multiple of 2. Thus p squared, and also, as a result, p is even. And so this means p is equal to 2k for an integer k. Then we can substitute the 2k here for p inside for p squared. And so what this p squared equals 2q squared will turn into will be 2k squared equals 2q squared. Thus, we have, if we simplify this down, it will turn into q squared is equal to 2k squared. And that tells us, like it did for p, that q is even. And so, is it possible to say that they're both even numbers and not contradict something that we already said? So, however, P and Q have no common factors. So they can't both be even because they'd have a common factor of 2. Thus, we'll say, thus, P and Q as evens is a contradiction. Therefore, we now have the ability to say that what we assumed from the beginning is wrong and the opposite is true. So at the very end, we can say, thus, by contradiction, square root of 2 must be irrational. So that's a full proof that shows that it's irrational here. Now this example here, we're going to prove that if x squared is irrational, then x is irrational. To approach this one, since it's an if-then, I'm going to actually apply the contrapositive to it. So think about the two parts here as P and Q. Our statement is P implies Q. The contrapositive would be the statement not Q implies not P. Or in other words, that would go, if x is rational, then x squared is rational. So let's do the proof on this one. We start off with the first part that says x is rational. So what we'll do is we'll say let x be a rational number. Since we're saying it's a rational number, we should be able by definition to write it in a certain way, which is x is equal to m over n for two integers m and n. Of course, with n not equal to 0. So now we start with x. We say x is this thing since it's a rational number. Then we'll go ahead and see if we can apply this to x squared. Thus, x squared would be m squared divided by n squared. And now, does this mean that x squared is rational? Well, we can verify that by just saying that since m squared and n squared are integers, if you square an integer, you still have an integer. And of course, the bottom part for n squared is still not equal to 0. We can say that x squared follows in the form of a rational number still, and so x squared is a rational number. And so by contrapositive, if we flip this back around to where we started, this would prove that the original statement is true. So this proves if x is irrational, then x squared is irrational. Now this statement says prove the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y for x, y in the real numbers. Okay, so let's make sure we understand the definition of absolute value. The definition of absolute value is x if x is greater than or equal to 0, or negative x if x is less than 0. The proof of this one is going to break down into cases. We have one case here if x is greater than or equal to 0 and y is greater than or equal to 0. A case 2 if x is greater than or equal to 0 but y is negative, less than 0. Or x could be less than 0, y can be greater than or equal to 0. Or they could both be less than 0. So depending on which of these cases, we have to check whether the original statement is true in all cases. So to start out the proof, what I'm going to do is say let x, y be real numbers inside the real number set. Case 1, we have x is greater than or equal to 0 and y greater than or equal to 0. Thus, x plus y is greater than or equal to 0. And also, by definition of the absolute value of x plus y, since they're both positive, their sum is also positive, and so the absolute value is still just equal to x plus y. And that's equal to the absolute value of x plus the absolute value of y, since again, they're equal to each other here by definition. And so as a result here, we can say thus absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. It's not less than, it still says equal to, but we can assume it's going to be one of the two. And thus for the next case, case 2, for this one we have x is greater than or equal to 0 and y is less than 0. Then as a result, x plus y is less than x plus 0. We can say this because obviously y is smaller than 0, so it's going to go on the smaller than side. And that's the same as just x. And since x is positive, it's equal to its absolute value of x. But the absolute value of x alone has to be less than or equal to the absolute value of x plus the absolute value of y. So now consider that negative x must be less than or equal to 0. And thus, we can say that negative x plus y, or is equal to negative x plus negative y, must be less than or equal to 0 plus negative y. And this is equal to the negative y, and since y is a negative number, that's equal to its absolute value of y, which has to be less than or equal to the absolute value of x plus the absolute value of y. So what we've shown here is that x plus y is less than or equal to absolute value of x plus absolute value of y, and negative x plus y is less than or equal to negative absolute value of x plus absolute value of y. This means the absolute value of x plus y has to be less than or equal to the absolute value of x plus the absolute value of y. So to be able to show that, I've had to show it for both the positive x plus y and the negative x plus y. Both of those are less than or equal to, and so it's true for the absolute value in this case. Case 3, we were going to consider that x is less than 0 and y is greater than or equal to 0. And so this is basically the same situation as the last case, but just switching around x and y. So if we switch x and y in the last case, we'll get the same thing. So that can tell us that case 3 is also verified as well. And then finally, for the last case, case 4, we're going to be dealing with x is less than 0 and y is less than 0. So now this is something different. Let's see how it works. In this case, the absolute value of x plus y, since they're both negative, in this case, or they're both less than 0, that'll be the same thing as negative x plus y, which is equal to negative x plus negative y. And negative x is equal to the absolute value of x, and same for y. Thus, in all cases, we have either less than or equal to. Thus, we can say that the absolute value of x plus y is less than the absolute value of x plus the absolute value of y for all those real numbers x, y in the real numbers. Now, the last example of the section says, for every n in the natural numbers, prove that n cubed plus n is even. Okay, now anytime we're approaching a problem where we have to show that something is even or odd or a multiple of something or divisible by something, we most of the time are going to have to work in cases, since it can break down into different things depending on what kind of number we have in the natural numbers. So I'm going to, just like the last one, I'm going to have to do proof by cases here. But we have to consider what cases are we dealing with. Well, it can either be even or it could be odd. There's only two cases here to work with. So to start off here, I'm going to start by defining what n is. N is a natural number. Okay, so that's, again, we have to start off with that part. For case 1, we're going to suppose n is even. Then, as a result, n is equal to 2k for some k in the natural numbers. And as a result, thus we can say that n cubed plus n, substituting n would give us 2k to the third plus 2k. That would be equal to 8k cubed plus 2k. And let's see if we can make this into a multiple of 2. Well, there's a common factor of 2. Everything's divisible by 2, so we could write that as 2 times 4k cubed plus k. And we can say that's a multiple of 2. Thus, in the first case, n cubed plus n is even. Now, if we look at case 2, we're going to do the same thing, but for odd. Suppose n is odd. Then how can we write our n by the general form of an odd number? Indeed, the general form of an odd number was 2k, or we'll use a different letter here, 2p plus 1 for p in the natural numbers. So if n looks like this, let's see what happens with n cubed plus n. Then n cubed plus n is equal to 2k plus 1 to the third plus 2k plus 1. I have to do some algebra here. You'll have to expand the 2k plus 1 to the third. And what I got was 8k to the third plus 12k squared plus 6k plus 1 plus 2k plus 1 on the very end there. And if we combine everything together, and we'll get 8k cubed plus 12k squared plus 8k plus 2. And do we recognize all of this as a multiple of 2? Indeed, everything is divisible by 2. We can rewrite that with a 2 in front to make that clear. And so, yes, indeed, we have this statement, which is a multiple of 2. And so we know that n cubed plus n is even in this case as well. And so, therefore, n cubed plus n is even for all n in the natural numbers.